Hello. We are going to present today sharding the data jigsaw puzzle. We are going to see sharding in practice, client-side field level encryption in action, and a Paychex story. This is Vishy Ganesh. I'm a software solution lead at Paychex working on SSO and federation strategies. You can reach me on Twitter at Visveshwar. I'm co-presenting this topic today with Chris Hilt. Chris?
Welcome, I am Chris Hill and I've worked for Paychex as an architect for the past 10 years. I was involved in the initial use of MongoDB at Paychex and have used MongoDB in many solutions since, including some of our most mission critical tax, financial, and authentication systems. But that's enough about me. Let's take a quick look at the agenda for today's discussion. I will start with a quick primer on what sharding is and the important concepts you need to know. Vishy will then take us through a demo of a sample application we built. He will also do a quick introduction on the new 4.2 feature, client-side field level encryption. Finally, we will share some details on how we use sharding here at Paychex and some lessons learned. Our goal is to share the knowledge we have built over the past few years at Paychex and give you an understanding of how sharding works and how it can be used to solve some real-world problems. With that knowledge, we are confident you will be able to better utilize sharding in your own application. Before jumping into MongoDB, I want to quickly introduce you to Paychex. We are a recognized leader in the payroll, human resources, and benefits outsourcing industry. The samples we will share today are based around the simple HR application involving clients and their employees. It will demonstrate some of the ways we use sharding and deal with sensitive data at Paychex. So let's start talking about the important concepts in sharding. So naturally, the question is, what is sharding? When you use MongoDB for the first time, you probably start with a single node. But how do we move beyond that single node? First, we introduce a replica set. A replica set makes MongoDB highly available. When you have multiple nodes in the replica set, they will share the same data. So if you look at the diagram or the slide on the left, when we add a new document that represents an employee to the replica set, that document will be copied to each node, 1, 2, and 3 in this example. If you lose one of the nodes, the replica set will continue to function because they each have a copy of the data. So what is sharding? Sharding is MongoDB's solution for data partitioning. A shard cluster is comprised of multiple replica sets. Each replica set in the cluster is known as a shard. Looking at the example on the right of the slide, a new document inserted into the shard cluster will be assigned to a single shard. In this case, the new employee document is assigned to shard A. Because shard A is a replica set with three nodes, that document will be replicated to all nodes in shard A, 1, 2, and 3. So why do you want to partition your data? There are a number of reasons of why you would shard. And going into detail will take more time than we have. But I wanted to quickly review some common reasons you introduce sharding. The most common reason to introduce sharding, horizontal scalability. Sharding lets us grow our data beyond what can be stored on a single MongoDB node. Another reason to shard is because you want control over where the data is located. For example, if you have data in the US and Europe, you might want to partition data by continent so each shard is physically close to the application that uses it. Another reason you might want to control where data is located is because you have replica sets with different hardware characteristics. For example, you might have a replica set with a lower cost storage for archive or higher I/O throughput for fast write transactions. Finally, you might create shards for resiliency reasons. So if you lose availability of a replica set, your cluster will continue to operate with a subset of data. Or you might choose to create a few shards to lessen the recovery time in a major BCP event. Each shard can be restored in parallel, significantly cutting down the overall restore time. So how does MongoDB decide which shard the document will be assigned to? In order to answer that, we need to introduce a few more concepts. So in MongoDB, you insert documents into collections, and collections are created inside of databases. The database in the shard cluster is assigned a primary shard. The primary shard is chosen by MongoDB to be the one with the least number of documents. Collections are unsharded by default and will reside on the database's primary shard. So if you look at the diagram on the right, the documents in the unsharded collection 2 are stored on shard A, which is the primary shard for the database. So let's review how a collection is sharded. To make a collection sharded, you define the shard key for the collection. The shard key is a set of fields you want to use to make sharding decisions. In this example, we have defined the shard key to be the field's name and age. The values AL and 18 on this document shown are called shard key values. So shard keys are the set of fields defined on the collection, while shard key values refer to the values for those fields on a specific document in the collection. One final definition we need to introduce, and then we can start putting all the pieces together. A chunk is a subset of documents identified by a contiguous range of shard key values. For example, if you have a single integer field as a shard key, a chunk might define the range between numbers 10 and 100, or a string from A to F. MongoDB will assign each chunk to a shard in the cluster, and the documents that fall into that chunk will reside on that shard. MongoDB will also create new chunks as your data set grows and move chunks around between shards to balance the data distribution. We're now ready to talk about different ways this assignment happens. So if you have a single field as a shard key, you can use hash sharding for the collection. With hash sharding, MongoDB will create a hash from the shard key value and create chunks based upon the hash. This helps spread data evenly across the shards, especially when using a monotonic shard key value. A monotonic value is one that always increases, such as a timestamp, numeric sequence, or UUID. With hash sharding, there is no guarantee that two documents in sequential shard key values will reside on the same shard. Using our previous example, if we use hash sharding on the age field, documents with ages 25 will all be on the same shard. Documents with age 26 will also be on the same shard, but documents with but the two documents may be assigned to different shards in the cluster. MongoDB will automatically manage the chunks for the hash values and assign those chunks to the shard. But many times you'll have multiple fields you want to use with a shard key. Another option is using range sharding. With range sharding, chunks are created directly from the shard key values. If you have multiple fields in your shard key, ordering is important, just as with indexes. The chunk key space will be defined by the first field and then the second, etc. So in the previous example, if we defined a range sharding strategy using name and age, the chunks will be created based on the alpha ranges on the name, followed by the numeric ranges on the age. Given this, people with the same age would likely be spread across the cluster. For example, Al and William, both age 26, can be assigned to different shards because A and W will be at opposite ends of the key space. As with hash sharding, MongoDB will manage the chunks and assignment of the chunks to the shards. So this really leads to a question: can I have control over what shard documents and where shard documents are assigned to? The answer is yes. And for this, we need to introduce zones to discuss how. Zones are tags created by you to help manage the assignment of documents in the collection to a shard. You can associate a single zone with one or more shards, and each shard can be associated with multiple zones. To map documents to zones, you create one or more zone ranges. A zone range maps a subset of shard key values to the zone. So using our previous example, if we had age as our shard key and you want to put all teenagers on shard A, you would create a zone called teenagers and associate that zone with shard A. You would also create a zone range that maps all ages from 13 to 20 to the zone teenagers. The zone range will be inclusive of the lower bound, 13 in this case, and exclusive of the upper bound, all ages less than 20. So let's take a step back and quickly review what we just learned. Documents are inserted into a collection, and that collection lives in a database. Collections are unsharded by default, and documents will reside on the primary shard for the database. To make a collection sharded, you define shard keys on the collection. Chunks are created based upon the shard key value ranges, and each chunk is assigned to a shard in the cluster. You can use hash sharding or range sharding to let MongoDB automatically distribute documents to the shards. If you want more control over that assignment, you create zones and associate the zones with the shards and map ranges of shard key values to individual zones in the cluster. Before we get to the demonstrations, I want to cover a few more topics. I promise it won't take too much longer, but these concepts are important, and the better you understand them, the more you'll get out of the demonstration. So, in the previous slides, we talked a lot about how data is stored in the cluster. I want to shift and quickly discuss additional components in the sharded cluster. The shards, or MongoDB instances, each contain a subset of the sharded data. But how does our application know what shards in the cluster to communicate with? It uses the config servers. The config servers are just another replica set in your cluster, but instead of storing your application's data, it stores documents that have metadata about the concepts we just talked about inside of a special database called config. A couple of examples of metadata are shards in the cluster with their host names and chunks for each collection and what shard they're assigned to. The third component we want to review is the router, or MongoS instance. The router sits between your application and the MongoDB cluster and coordinates with the config servers and shards to run your updates and queries. Your application does not need to know the details of what metadata is available in the config server, nor figure out what shards to communicate with. Your application only interacts with the router, just like it would with a single database or replica set in MongoDB, and the router does the rest. If you have a query that needs to run against multiple shards in the cluster, the query router will communicate with each of the shards behind the scenes and combine the results into a single stream back to your application. You will see these components in action in our demo in a few minutes. At this point, we've covered how sharding works, why you use sharding, and the components in the sharded cluster. The final topic I want to talk about is choosing a shard key. So why do you really need to think about the shard key and how you choose it? There are a few reasons that come to mind. A collection may only have one shard key. So the key you choose will apply to all documents in that collection. And also, once you choose the shard key, it cannot be changed later. Prior to MongoDB 4.2, you also couldn't change the shard key values for any document. So for example, if you added all fields to the shard key, then all documents would be immutable. And the final reason, but probably most important one, is that poorly chosen shard key can affect performance, efficiency, and scalability of the cluster. So we're going to quickly review the four major aspects that you need to think about when choosing shard keys: cardinality, right scaling, query isolation, and reliability. Okay. You want to choose a shard key that has a wide range of possible value, ideally millions or more. Make sure you consider the range of values your application will use. For example, if you have an integer field, it on its own has an infinite number of values. But if you have an age field on your document that's an integer, The effective range of values your application will insert is closer to 100. Or if your application always inserts the same value into a string, all your documents will reside on a single shard. And that's regardless of how many shards you add to the cluster. Having multiple fields on your shard key will increase the number of possible values, as the key range is defined by all the possible values for all fields in the shard key. So when working with zones or range sharding, always look to add a field that has a high cardinality value. The next aspect to think about is write scaling. Try to use a shard key so that writes don't always target a single shard. A monotonic shard key value can cause a significant bottleneck on high volume inserts, as the writes will always be assigned to the shard with the max key chunk, causing one shard to remain busy even though the other shards are idle. Try to avoid monotonic shard key values whenever possible. Another consideration is geographic sharding if your replica set spans a large geographic area, because writes will always be faster when the nodes are physically closer. Almost opposite the write scaling, you want queries to target a single or small number of shards. If your queries have to span multiple shards, your MongoS router will need to combine the results from multiple replica sets prior to returning data to your application. This can be especially impactful to performance when you sort on one of those fields. This isn't just a consideration for choosing your shard key. You need to keep this in mind when creating queries in your application code. Try to include as many of the values in the shard key as possible in your queries, as this will help the query router target a single node if possible. And the final aspect we need to think about is reliability. Do you want your application to continue to function in some capacity when the replica set fails? In the shard cluster, the remaining shards can continue to accept query and write operations. If you want more control over where data is available in the failure, consider using zones. Also think about your recovery time objectives. If your application needs to restore quickly in a major BCP event, having multiple shards can lessen that time for recovery. Okay, so we're going to do a quick concepts review of all the things we talked about. So we've talked about reasons to use sharding, such as to grow your data beyond the capacity of a single node. You also might use sharding to increase resiliency of your application, or to have more control over where the data lives. You want to use range sharding or hash sharding to let MongoDB manage the partitioning of your data. If you need more control over what shards data is stored on, introduce zones and zone ranges. We did review the components of a sharded cluster. Shards store your application data. Config servers store metadata about the cluster, and routers eliminate the need for your application to know how to interact with the multiple shards in your cluster. Finally, we discussed some approaches to choosing the right shard key. You'll want to consider the cardinality of the shard key values, how you can isolate writes and queries, and take into account reliability of your data. I'm now ready to hand off the presentation to Vishy to start our demonstration phase.
Thank you, Chris. We're going through a sharding demo with a new made-up product and implement the principles which Chris has shared with us over the past few slides. So here's a use case that we're going to work with. We are building a SaaS product called Global HR, for which we have to implement a few basic requirements. Geographic restriction is one of the requirements we have to meet because we have data restriction laws and we want to be performant when we access data within a region. We are also offering two versions of our product, Premium and Standard. There is a requirement for PII data encryption, and we have data retention policies that we'll have to adhere to. For this demonstration, we stood up multiple Kubernetes nodes across US and Europe. We have stateful data sets for US Premium, US Archive, and US standard shards, and similarly for Europe. The application is hosted in 3 data centers, and the configuration for the application is controlled via config maps and secrets. As Chris described, a sharded cluster has only one replica set, one config replica set, and one or more shards. The config replica set spans both geographies and has metadata of all the shards located in this particular cluster. The application communicates with the shards through a Mongo S, that is the query router, and the Mongo S obtains its metadata from the Mongo config replica set. So for the purposes of this project, we have 2 collections, client and employee. These collections capture the attributes that will be used during sharding. For example, premium, active, region, and client. We'll be going through how we're going to use these attributes in the coming slides. So let's go back to our requirements, right? So the first requirement was Geo Sharding. For Geo Sharding, we are going to use the region as one of the shard keys to differentiate between documents. Geo Sharding gives us multiple benefits. It allows the data to be closer to the application, and it will also fulfill regional data laws where applicable. The second concept that we wanted to fulfill was standard versus premium. This was a feature set requested by product. Standard is going to be free, but will have the same feature sets as that of premium. But from a build perspective, premium will have higher availability characteristics, higher I/O throughput by running on a different class of hardware, example SSDs, and cross-region availability. Let's look at a build out we did for this project. So as you can see, premium is available both in Azure East and Azure West with 5 nodes spread across both availability zones. A standard is only a 3-node replica set with 2 nodes in US West and 1 node in US East. And the archive is again a 5-node replica set with 3 nodes in US West and 2 nodes in US East. But standard and archive will be running on lower cost storage hardware. So based on an initial rollout, our footprint in Europe is going to be pretty small, so we just have 1 availability zone. To implement our premium versus standard, we have a tag on our document called premium, which will be used to signify the premium clients. Data archiving. We generally pay the price by mixing both classes of data, active and inactive data, in one database, which ends up slowing the throughput for actively used data. One way to get past this hurdle is to move the inactive data to a different shard. This can be used for reporting purposes or just for data retention purposes. We are going to achieve this by tagging our documents with an active flag, which will be used to indicate whether this particular client is active or inactive. So to summarize, we've chosen premium, active, and region as our shard keys. But note, these all have very low cardinality. So to increase the cardinality, we also will be adding client ID to our shard key. Now let's look at a demo. So for the demo, we're going to cover the following aspects. We're going to create zones, add shards to the zone, shard the client collection. We're going to look at the config server database. We're going to search for a client and demonstrate query isolation, migrate data across premium and standard and view the actual migration, and try to retrieve data across geographies. So I have a script which I've written, which kind of will help us go through this demo in a more streamlined fashion. So we're going to initialize the database. We're going to have a database called client. We're going to clear the database by dropping it. We're going to load data from a test file. It's just called client.json. We have all our data in there. And this is where things kind of get interesting. We're going to initialize our shards with zones. So essentially what we're doing is we're adding a shard tag, which is nothing but our replica set name, to a particular zone. So US standard RS goes to USS and US premium RS goes to USP. And similarly for US and Europe. The next step is we enable sharding on the database itself, which is fulfilled by sh enable sharding. We then create an index matching the shard key. So we have region, active, premium, and the client ID, which forms the index. And we finally shard our collection with the same properties, which is region, active, premium, and the client ID. So let's now see how we can introduce range sharding targeting a particular zone, as Chris had highlighted during the concept part of this presentation. So let's take a US standard zone, right? So what is the US standard zone going to have? So the region is going to be US. It's going to have active clients, but they're not going to be premium clients. So this is going to span the full range of client ID, that is from min key to max key. Let's look at the same thing for premium. The region is US. They are active clients. It is premium, is true, and across the range. When it comes to our archive ranges, we are going to have the region is going to be US. We are not going to take into consideration whether it's premium or non-premium. So both the premium and the non-premium, if they are inactive, will be going to the US archive shard. So let's just run this on our database. Okay. So we've got this executed on our database. So the first thing which we're going to have a look at is the config database. So the config database, as Chris described, has the metadata with respect to this particular cluster. So for example, when we look at the shards collection, it has a list of all the shards that we have for this particular cluster and the hosts which map to those particular replica sets. We also have the tags which we just created. For example, let's look at the EU archive tag. So the EU archive tag has the region EU with inactive clients and which are not premium, and also inactive clients from EU which are premium, and so on and so forth. So we have the EU standard, EU premium, and all the US tags. Let's get back to the client, right? So we've loaded our clients from the client list. So we have the client ID, the name, and the other attributes as what we discussed. So we're going to take one particular client ID, right? So we're going to take this particular client ID, and let's actually just query for this client ID and see how Mongo goes about querying this particular client. So when we queried this particular client without the shard keys, we ended up querying this particular client across 6 shards. And this does not get us anywhere close to query isolation. So to be able to isolate our query down to 1 shard, we are going to query this client ID on the US region with premium true and active true. So with this, we are able to see that we were able to narrow down our query down to just 1 shard, thereby achieving query isolation. So let's go back to our list of tasks we wanted to go through. So we have created zones, added shards to the zone, sharded the client collection, viewed the config database, searched for the client, and demonstrated query isolation. Now let's migrate data across premium and standard and see how does data move across shards. So we have a quick Postman project which captures the, which has the request which we want to do to migrate data. And we also have a simple GraphQL chain stream, which is going to capture the data moving across the, let's restart this, which is going to capture the data moving across the shards. So let's first query this client. So this client is not a premium client, right? So the premium is false. So let's migrate this client and make it premium. So what's going to happen right now is the client is actually going to move across from the standard shard to the premium shard, and you're going to see a change stream event occurring where it deleted the record from the standard shard and it inserted this client into the premium shard. Let's try it again. So let's now move it back from standard into from premium into standard. So you're going to see two events, one event to delete the client from premium and insert the client into standard. So we have inserted the client into standard, and we're going to see change for delete, which is going to delete it from premium. So with this, we have seamlessly moved data across shards, which would have been a very monumental task to move data like this in a live fashion across databases. So the last thing is we're going to try to retrieve data across geographies to illustrate the sharding feature where we can isolate data to a particular geography. So in this case, we have queried this particular client from East. So we're able to see this particular client. So this is US East. So the country is USA. Now let's query the same client from Europe. So when we query the same client from Europe, we would not have access to the data because we have introduced geo restriction, thereby making this particular data inaccessible from the Europe region. All right. So now let's get back to where we left off in the presentation. So we've looked at sharding demo. So now let's look at an emerging feature in MongoDB called client-side field level encryption. So as the name indicates, client-side field level encryption is essentially encrypting data in the documents at a field level. So why Mongo client-side field level encryption? We're going to look at how client-side field level encryption is different from other strategies which are already available with MongoDB. We then are going to see how is client-side field level encryption achieved using envelope encryption. We're then going to see how does MongoDB help us to get there faster with automatic encryption. And the last, we're going to see a real-world example where client-side field level encryption is used, and we can see it in action. So Mongo documentation does a great job in illustrating a matrix of security considerations at a data tier. So let's start with the left side of the matrix. So these are the vulnerabilities that we have today: database privilege abuse, network snooping, data theft, and access to the memory of a data host. Now, these vulnerabilities can be addressed on a case-by-case basis. For example, role-based access control can address database privilege abuse. TLS network transport encryption can address network snooping. Encryption at rest can prevent data theft. But client-side field level encryption gives us a cross-cutting implementation with all these features. Envelope encryption. So this is not new. This is pretty standard practice. So what does envelope encryption entail? We essentially encrypt a plain text with a data key and then encrypt the data key with another key called master key. The encrypted data key is stored on a Mongo database, which can co-reside with the data. And the master key is generally held by a key management system. Mongo currently supports the Azure Web Services Key Management System. Now let's look at how data is accessed. So the driver actually accesses the data encryption key from the database which holds that. We then take the encrypted data key and decrypt it against the key management system. Once the data is retrieved, we can decrypt the data using the data encryption key. What this has achieved is the data is in its encrypted form right till the application. Only the application that possesses access to the data encryption key database and to the key management system can read the particular data which we have accessed. The Mongo driver does the heavy lifting of this access coordination. There's another talk by Kenneth White during this conference, which will go into details of client-side fee-level encryption. Automatic encryption. This is an enterprise-only feature. The driver takes care to encrypt, decrypt, and coordinate with the key stores. This can also be achieved with the community edition, but the application will be responsible for the encryption and decryption. Client-side field-level encryption in action. So, as we were preparing for the demo, we built out our clusters in Azure and didn't lock down the clusters to begin with. Securing the clusters was going to be our next task. Meanwhile, I started testing the application for client-side field-level encryption. Chris comes back the next day and notices that our data is gone. We have a ransom document, literally a Mongo ransom document, requesting us to pay 0.1 Bitcoins to get all our data back. So what did the hackers actually get access to? They got access to the names and the employee IDs and the country where the employee actually resides. But they did not get access to any of the PII because the data in itself was encrypted, and the hackers did not have access to the master key and to the data encryption key. So we wanted to share this real-world example with you, which just fell into our lap as we were preparing for the demonstration. So how does global HR use client-side field-level encryption? We encrypt the employee fields like SSN, blood type, salary, and phone number. So there are two kinds of encryption which we could do. One is deterministic and random or non-deterministic. So SSN and phone number we have deemed as deterministic because we want to be able to query back through the application on these fields, whereas blood type and salary are fields which we have considered to be random, which we are never going to query back on. So let's look at a sample schema and then see client-side field-level encryption in action. So this is the encryption schema which we use. This looks like the JSON schema which we use for MongoDB, but is not the same. So as you can see here, when we build our schema, we indicate that the SSN to be deterministic and our a blood type to be a random encryption type. So this is just a simple helper function which helps define the schema. And how this actually fulfills auto encryption is we just hand over this particular schema to the auto encryption settings, and thereby the driver then takes over to encrypt or decrypt the data on the fly. So let's see a demo for client-side field-level encryption. We're going to show client-side field-level encryption, employee, how it looks in the database, and how does the SSN and other attributes query from the database. So to begin with, we're going to create a client, create an employee on this particular client ID. Right? So let's create a Joe Bean on SSN 34, give him a salary of 400,000. So we're going to create that. So we got an employee. So let's look at this employee. Yep, we were able to retrieve the employee. The first name, SSN is 34, and all the other attributes. Now let's look at the client, the same employee in the database. Right, so if you notice, all the attributes are actually encrypted now. The SSN, blood type, phone number, and the salary. And if you try to query on any of those attributes, say SSN, if you remember, we had set it to 34, you're not going to get back any details. So with this, we complete the demonstration for client-side field-level encryption. So let's get back to the presentation. So we have all the code for this project shared on GitHub. This includes the Kubernetes build-out scripts, the local Mongo cluster build-out, demo data, which we use for this project, and the sharding scripts, which we used for this project. In addition, we also have demo code for client-side fee-level encryption for the community edition and enterprise edition as a standalone project. Sharding at Paychex. Our journey has had a fair share of bumps and triumphs with sharding. We wanted to share a quick set of tips and obstacles that we faced through this process. As developers, it's critical that we run a sharded cluster locally. This can be achieved by running a cluster using containers. The example code has a script to be able to run a sharded cluster locally. Always validate the sharding strategy at design time. It is very critical that we kind of get the sharding strategy pinned as early as possible. Test your shard key resolutions locally. And always remember that you have to eventually query what you've inserted. So access to the shard key values is critical both at read and at the time of write. So with this, I hand it back over to Chris.
Okay, thank you, Vishy. Okay, next I wanted to share our some of our Geo Sharding strategy we use here at Paychex, and there are some common patterns we use. Most of them primarily focus on resiliency attributes of the data we store in it. So on the screen is the first replica set pattern. It is a data center HA pattern. With this, applications are deployed to each data center and interact with a replica set that's really isolated to that data center. Because we have multiple nodes all running in the same data center, typically a minimum of 3, we are resilient to single node failures. The diagram shown here illustrates 2 data centers in US East. The application deployed to the first data center and uses the replica set is shown in green. And red shows the same configuration, but in the second data center. Examples of where we might use this pattern are local sessions and temporary work output. So the next pattern I want to share is the regional US pattern. With this, our applications are written to run independently within a single region. Although they may use data from the other regions, they don't rely on it. So looking at the diagram, we have 2 regions, US East and US West. We deploy a replica set for each region. In this case, green is shown the US East replica set, and red shows the US West. We have 2 nodes in the primary region, and we also throw the 3rd node in the other region for each replica set. Through zone sharding, our application is configured to interact with the local region's replica set. This allows the application to continue running in both regions, even if we lose an entire data center. It also allows the application to remain available in a global sense when one region fails and the other doesn't. The 3rd replica set pattern we use is what I call the global US high availability. We split the nodes in a single shard across 3 regions. 2 primary regions, as shown here, US East and US West. And because even numbers aren't a good thing with MongoDB, we introduce a 3rd region and put at least 1 node in that. So the minimum number of nodes in this configuration is 5. And then we deploy our application in multiple regions, multiple data centers, and it interacts with that single replica set. So updates will cross regions depending on where the primary node is for the replica set. And we use this pattern when we need consistent data globally across the US, but we can also accept the performance hit of those cross-region writes. Okay, so as part of sharing our experiences, we also wanted to share some things we learned and many times the hard way ourselves. So the first lesson learned is about shard keys and shard key values. We talked about them earlier in the presentation. They have very different meanings, and case in point, there's a new feature in Mongo 4.2 that lets you alter the shard key values. We totally misread the documentation, and we thought it allowed us to change the shard key on the collection. We're very excited because we are going through a transformation where we have to change the shard key on some of our collections right now. And you can imagine we were equally disappointed when we realized our mistake in interpretation, and we could not change the shard key, but for those collections. So the documentation uses the term shard key and shard key value many times. Make sure you know which one the documentation is talking about when reading about behaviors and features. And this leads us into our second lesson learned. Changing the shard key without downtime is not trivial. If you look at the Mongo documentation, they give a process to actually make this change. They tell you to export the data from your current collection, create a new collection with the new shard keys, re-import the data, and then drop the old collection. That is an acceptable process to go through. However, it will involve downtime for your application because your application is dependent on a single collection, and at different points in this process, the collection will go away. So we do have a mission critical application that needs to change the shard keys, and we can't accept downtime. So our application has to manage this move. So we now need the application to know about the two collections simultaneously, know how to read from both the new one and look for documents in the old one if it can't find things, make sure all rights go to the new collection, and then we can write processes that in the background start moving documents over from the old to the new. And then once we're done with all this move, the documents are all in the new collection and we're satisfied we haven't lost anything, we have to redeploy the software to remove knowledge of that old collection before we can actually drop it. So it's manageable, but it's not trivial. So our recommendation is to put as much foresight into choosing your shard keys as you can early in the process. Another lesson learned is thinking and talking about read and write characteristics early in the design. We talked a lot about how to choose a shard key, but we didn't talk about read and write characteristics at all. For example, if you go back a few slides to our global US pattern, where the replica set is spread across the US, if we choose to do a write majority, we need to write data to multiple regions before committing. Now, our application can choose to say, I'll do a write to versus a write majority, which in that previous design would keep the write within a single region, but that also opens you up to data loss if there's a major BCP event where you lose those data centers in that region at that time. So make sure early in design, you also discuss availability requirements, performance metrics, and your acceptance of data loss in the major BCP event. And the final lesson learned, as Vishy demonstrated earlier, use the explain plan in the Mongo Compass tool to make sure your queries are targeting the right shards. This will really help make sure your application is performing to its peak. And I guess that ends our demonstration, and I want to thank you for your time and listening. We hope you have enjoyed hearing our Paychex story and how you can better use sharding in your own application. So thank you.